We will be talking about bonding, and specifically, we're going to talk about covalent bonding, ionic bonding, how covalent bonds form. And this is a very good intro for this chapter since we're going to be discussing bonding for the most part in chapters 8 and 9. And let's start with chemical bond formation. So, in general, chemical bonds are defined as a force of attraction between atoms or ions. Now, chemical bonds can be formed between two atoms, either through sharing, and this involves sharing here involves covalent bonding, which is between two nonmetals, while transfer of electron occurs between a metal and nonmetal to give us ionic bonding. Now, covalent bonding can either also be nonpolar or polar. And this is already discussed in the video of polarity or ionic bonding. And these two will be determined by differences in electronegativity, but this is not the focus of this video. Now, atoms, the main purpose of atoms forming chemical bonds is to really form a stable system in which the overall energy is at its lowest. So the goal here is to always lower the potential energy of the system. And right here, we're going to discuss this plot of potential energy versus the distance when two hydrogen atoms come together to form a diatomic hydrogen molecule. So there are, if you notice on this plot right here, there are four regions. We're going to go through them one by one and deconstruct together what does each step mean. So in region 1, note that the two hydrogen atoms are further apart from each other. In the second step right here, so we're reading it from right to left, note that the energy here is still high. And as we move to step 2 and the electron clouds of the two hydrogen atoms overlap, right, the energy begins to be a little bit lower. In this particular phase, there is electron, and nucleus to repulsion as these two atoms are trying to get closer to each other. Now, as we move further to step 3, note that the energy now is getting to a minimum right here at step 3. And in this phase, the electron nucleus interaction, it overweighs the electron, and nucleus repulsion. So what happens is the nucleus of one hydrogen atom is attracted to the electron of the opposite hydrogen atom, and then vice versa. So this here is responsible for the formation of the bond. Now note that because this has the lowest energy, this has the lowest or most negative potential energy. Now, if you try to get these, if these two atoms were brought even together, even closer, right here, that means that so there will be more nucleus and electron repulsion that outweighs that attraction. So this is here what we call our sweet spot at step 3. Another thing that is very useful and will come later when we talk about bond length is note that this dip right here not only represents the most stable or the lowest potential energy, it also represents the internuclear distance, or the distance between the two nuclei of the hydrogen atom, which represents the bond length. And of course, as low or as more negative or lower in potential energy, this gets, that means the stronger the bond is going to be, and vice versa. The higher the potential energy right here means that the weaker the bond becomes. Now, the second type of bonding we're going to talk about is ionic bonding, and we'll be focusing here on lattice energy. So ionic compounds, as a reminder, do not form molecules. They form, so because molecules are discrete, they tend to form crystalline solids. So this is, for example, the sodium chloride. So sodium and chloride ions coming together, which is an ionic compound, to form a crystal lattice. As a reminder, in a crystal lattice, you have your cations, and anions are going to be formed in a very ordered, strategic way to maintain the charge neutrality of the compound. All right. And this brings us to the definition of lattice energy. So lattice energy is the energy that's going to be released when the cation and anion, or 1 mole of gaseous cations and anions, combine to give us 1 mole of crystalline solids. And as a reminder, these measurements are done in the gas phase, and this is why gases are the gaseous cations and anions are reference. Now, lattice energy is always an exothermic value, means that it is a negative value for a cation and anion coming together. And how can we use now the values of lattice energies, or if you are given a different ionic compounds, how you can rank them based on lattice energy? Well, lattice energy gives us an estimate of the strength of the ionic bond. So the stronger the ionic bond, the higher the more negative the lattice energy is going to be. Now, lattice energy can be given by this equation right here. So this is the C here is the charge, and N plus and N minus are the ionic charges, the cation and anion, and D is the interionic distance. And based on this formula for lattice energy, we can say that as charges on the ions become larger, right, the more exothermic and the stronger the ionic bond is going to be. And as the ionic sizes become smaller, again, the more exothermic or the stronger the ionic bond is going to be. Now, between these two factors, ionic charges are more important than the ionic size. All right. And right here is a very good comparison between something like sodium fluoride and calcium oxide. Note that the charges and the ionic sizes are also different. Calcium is higher in charge than sodium, so as oxide versus the fluoride. And note that there is a larger difference, actually a very large difference in the magnitudes of the lattice energies between calcium oxide, and all that goes to say that ionic charges are very important. Now let's also look at trends in lattice energy and how we can relate them back to the periodic table. We can say that so for example, here are a series of compound. Note that the cations are group 1 metal cations, and just for the purpose of illustration, the anion is left to be a chloride, and we can say that as the ion, as we go from top to bottom in a group, that means that the ionic radius increases and the lattice energy will become less exothermic. So again, right here, look at lithium from lithium chloride, which is more negative or more exothermic compared to something like cesium chloride. And the reason for that is as the ionic sizes become larger, the distance between the nuclei of the cation and anion becomes further, so that further weakens the bond versus something like lithium and chloride. Because of the smaller size of lithium, it is able to get closer to the nucleus on the chloride ion. Now, let's see if we can apply this idea of lattice energy qualitatively, to arrange the following compounds, ionic compounds, in order of increasing magnitude. So from least to most exothermic using lattice energy. And we can look here and find out that we have here, we said charges are more important than size. So we have here for potassium and bromide, 1 plus 1 minus, 1 plus 1 minus, okay? And then for calcium and strontium, we have here 2 plus 2 minus, 2 plus and 2 minus. All right, so that means that the lattice energy probably of potassium chloride and potassium bromide is going to be lower compared to calcium oxide and strontium oxide. Now, if we are looking at potassium and bromide, say this is group 17. So we have here chloride and then bromide. So the lowest or least amount or least exothermic lattice energy is going to be potassium bromide and then going to be potassium chloride. So this has a larger ionic size compared to the chloride. And then let's look at calcium oxide and strontium oxide. So if this is group 2 metals, we have here calcium, barium, and then strontium. So strontium right here is larger than calcium oxide. So that means that, and they're both a 2 plus charge, so it'll be a strontium oxide, and then the most exothermic lattice energy will be for the calcium oxide. Now I want to encourage you to work on this problem using the same ideas that we utilized before, and let's look at placing these ionic compounds. So the first thing you want to really think about when you're looking at the problem of thinking it through, what compound am I looking at, right? First of all, is it a molecule, meaning that it's only nonmetals, or is it a formula unit, meaning that it is an ionic compound consisting of a metal and a nonmetal, as in the ionic compounds that were given? And then you want to think of, okay, that means that if I am looking at a magnitude of something, it means that it's lattice energy, because sometimes on assignments or on the exam, we don't explicitly say it, so you have to be careful. And the last thing I want to say here is let's look at these compounds and decreasing magnitude. So from the most exothermic or the strongest ionic bond to the least exothermic. Okay, now let's look at each one of them, and let's look at the charges. So I have here 1 plus 2 minus, 1 plus 2 minus, and here 1 plus 2 minus. So they all have the cations with a 1 plus charge and the anion with a minus 2 charge. So in this case, we will look at the sizes. Now for group 1 metals, we have here lithium, and then sodium, and then potassium. So that means that the lithium is going to be the one with the smallest ionic radii. And then let's look between oxygen and sulfur. So we have here, this is group 16. So we have here oxygen, sulfur. So oxygen is still smaller. So oxide will be smaller than the sulfide. So in this case, lithium oxide will be the highest or most exothermic, followed by potassium oxide, and then rubidium is just going to be at the very end, so going to be rubidium sulfide. And let's look which one is it going to fit with. It's going to be the first choice, choice A.